Hello everyone and welcome. In this video, we're interested in finding particular solutions of the Laplace equation that are called radial solutions. So first of all, we're going to denote our equation by E. Here n is the dimension, and the dimension here of our Euclidean space is at least 2. Okay, so by radial solution, we mean a solution that can be written as u of x equals f of r, where r is a function defined on the set of all non-negative real numbers or the set of positive real numbers. It really depends. Okay, so we want to translate this partial differential equation into an ODE that we're going to solve. So we're going to pick an integer k that is between 1 and n. And we're going to assume that we have a radial solution that is given by u of x equals f of r. Okay, so now we want to compute some partial derivatives here. We're going to compute the partial derivative of r with respect to xk. And this is equal to xk over r. We can also compute the second partial derivative of r with respect to xk. It's going to be the partial derivative of the first partial derivative of r with respect to xk. And using the product rule, we're going to get 1 over r minus xk squared over r cubed. Now, we want to find the partial derivative of u with respect to xk in terms of f. Now, we just use the chain rule here. We're going to differentiate f with respect to r. And because r depends on xk, we have to differentiate r with respect to xk. Now we can find the second partial derivative of u with respect to xk. And it's going to be equal to the partial derivative with respect to xk of f prime of r times the partial derivative of r with respect to xk. Now we apply the product rule. Okay, by applying the product rule, this is what we're going to get. Now for the partial derivative of f prime of r with respect to xk, we're going to apply the chain rule. And for the partial derivative of r with respect to xk and the second partial derivative of r with respect to xk, we're just going to replace with what we already got up there. So we're going to get the following. Okay, so applying the chain rule, and now we just replace. Okay, so we're going to get xk squared over r squared times f double prime plus 1 over r minus xk squared over r cubed times f prime of r. Now we want to simplify the Laplace of u. Okay, so the Laplace of u is equal to the sum, as k goes from 1 to n, of the second partial derivative of u with respect to xk. Now we just replace that by this quantity here. Now the sum, as k goes from 1 to n, of xk squared is simply r squared. So we're going to get the following. And r squared over r squared is just 1, while r squared over r cubed is just 1 over r. And we end up with the Laplace of u equals f double prime plus n minus 1 over r times f prime of r. Okay, so now we can see that the original PDE, so the partial differential equation, the Laplace of u of x equals 0 is now equivalent to an ODE, because now we have a function of a single variable f that satisfies the following equation. So it's a differential equation, an ordinary differential equation that is separable. Now we can also note that this equation will admit any constant function as a solution. So we're going to exclude all the constant function to begin with. Okay, now we want to find all non-constant solutions. Okay, to find all non-constant solutions, the first thing to do is to bring all the unknown on one side and the independent variable on the other side. Okay, so that's what we're going to get. We're going to get f double prime of r over f prime of r equals negative n minus 1 over r. Then we integrate with respect to r. Okay, as we integrate with respect to r, on the left hand side we're going to get a logarithm. On the right hand side we're also going to get a logarithm. Okay, so we're going to get the logarithm of the absolute value of f prime of r equals the logarithm of a minus n minus 1 logarithm of r. And here we can assume that a is greater than 0. Okay, now if we undo the logarithm by using the exponential, we're going to get the following. We're going to get that the absolute value of f prime of r is equal to a over r to the n minus 1. Or simply that f prime of r is equal to plus or minus a over r to the n minus 1. Now we can integrate this again. As we integrate, now we have to distinguish two cases. The first case will be when n is equal to 2, because we're going to have a over r. We know that an antiderivative of a over r is given by a times the natural log of r. So we have to distinguish two cases, n equals 2 and n greater than, strictly greater than 2. Okay, so by integrating, we're going to get that f of r is equal to plus or minus a times natural log of r plus b if n is equal to 2, and plus or minus a over n minus 2 times r to the n minus 2 plus b. And here, n is greater than or equal to 3. Of course, b is a constant. Okay, so now we can say that by including all the constant solutions, because we excluded them at the beginning, now we're going to include them in our final solution. So by including all the constant solutions and the non-constant solutions, combining those together, we're going to get that f of r is equal to c1 times ln of r plus c2 if n, the dimension, is equal to 2, and f of r is equal to c1 over n minus 2 times r to the n minus 2 plus c2 for n greater than or equal to 3, and c1 and c2 are arbitrary constant. This is the end of the video. Thank you for watching. Please consider subscribing, liking, and I'll see you next time. Bye.